Chapter 10 in our textbook deals with gases and their properties and behaviors, so we're going to spend the next couple of lectures talking about that topic. The kinds of gases that we're going to run across in our daily lives, as far as those that are involved in our atmosphere, the ones that we breathe in and out every day, for the most part are listed here, at least the ones that make up any noticeable amount of our atmosphere. The largest component, some people don't realize this, they think about oxygen being the atmospheric gas, but most of the molecules that run into your skin on a daily basis and that you breathe in on a daily basis are nitrogen molecules, a little over 78%. Oxygen is the second most common gas in our atmosphere, a little bit over 21%. So nitrogen and oxygen, if we consider dry air, if we ignore humidity, make up just about 99% of our atmosphere. And CO2 is not the next most common gas. If we're counting molecules or volume, argon makes up almost all of that last percent. And then you see CO2, neon, helium, methane, and krypton making up most of the rest of it. Now that doesn't mean those are the only gases that we run across, but any other gases that exist in our atmosphere make up less than this percentage, less than a part per million of our breathing air. You can look down this column. This is percent by mass. It's a little bit different than percent by volume as it works out, and we're going to talk about why later in this lecture, later in this series. Volume percent and molecules percent for gases, not for other compounds, but for gases, are the same thing. A little bit of a molecular view of gases, and this is an inaccurate molecular view, and I'll talk about why in a moment, but it does a good job of giving us an idea of what's going on. A gas is a large collection of particles that are moving around at random in a place that's primarily space. So the thing that's inaccurate about these drawings of how collisions work and how gases move around in space is that compared to the size of the space between them, gas molecules are actually much, much smaller than this. Molecules take up far less than 1% of the space in a container that they're in at normal pressures. And so we would, if we were to compare gas molecules to the size of a normal size container, the molecules would be much, much smaller than that compared to the space between them. So the question comes up, why does the atmosphere push pressure against us, and how much pressure does it place against us? And the reason it pushes pressure against us, the atmosphere does, is because of weight. The gas molecules that are above us have a certain amount of weight to them, and if we add up the masses of all of the gases that are on top of us, it turns out that a square meter of gas then multiplied by the height of our atmosphere gives you 10,300 kilograms. So if we multiply that mass by acceleration that's due to gravity to get a unit of weight, of force, and then divide by area, we find out that the pressure is 101,000 newtons per square meter, or kilogram meters per second squared per meter squared. And what that works out to, if we do the unit conversions on it, is 14.7 pounds per square inch. Now try to hold up something that weighs 15 pounds with just the last digit on your index finger. That's about a square inch. And it will feel extremely, extremely heavy, but what you're holding at that point is not just the weight of that object. You're holding the weight of that object and the air above it. But even without that object on there, your skin is dealing with, all the time, 14.7 pounds per square inch. And it's good for you that it is, because if it weren't, if there weren't 14.7 or something close to that pounds per square inch of air pushing against your skin, the pressure that's caused by the fluids and so on that are inside of your body would push out, and your body would actually, in some ways, explode. So we measure air pressure outside using a device that takes all of this into account. So the diagram that we have here represents a mercury barometer, and we have one of these. I have to see where we moved it to when we rearranged the stockroom. But we have one of these in the stockroom. I can show you during lab one day if you'd like. It's a pool of mercury, and then we take a tube full of mercury, full all the way, and stand it up inside of that mercury bath. And if we do that with a tube that's less than 30 inches tall, then the tube will stay full of mercury. And you may have done this in the bathtub or in the pool when you were a kid. You take a bucket, you put it under water, you fill it up with water, you turn the bucket over underwater, and you start to lift it out. And as long as the mouth of the bucket stays below the surface of the water, no air gets in, and this thing stays full all the way to the top. But notice we have a space here, because if we get greater than 29.9 inches of height, or 760 millimeters, that works out to, then the atmospheric pressure pressing against the water is not enough to overcome the amount of weight of mercury that's in the column, and the column mercury starts to drop out, and we don't get air here. This is empty space, vacuum. The only thing that might be in here is a little bit of evaporated mercury, but mercury's got a very, very low vapor pressure, very, very low evaporation rate, so there won't be much of that in there. That's going to be mostly open space right here. Now, if there's less pressure, if the pressure outside for some reason goes down, pressing against this, then that pressure is part of what's holding up this thing, and the column will drop, and we'll have a lower reading. And the amount that it drops by will be directly proportional to how much the pressure dropped. And so we can do a direct conversion and say 101,300 pascals is 760 millimeters of mercury, or 29.9 inches of mercury, or 14.7 pounds per square inch, or one of the chemist's favorite units for pressure, 1 atmosphere. So that is a mercury barometer, or a Torricellian barometer, since Torricelli was the inventor of this instrument. A manometer works a little bit differently in that it's measuring something different. A manometer is something you might use, say, to measure pressure inside of a tire. Let's say this bulb is your tire and it's got a certain amount of pressure. If we open up the valve, let's pretend this is the valve stem, open up the barrier between this and this tube of mercury, the amount of pressure that's in this gas will press against this side of the mercury, and an atmospheric pressure presses against this side. So on this particular manometer, what we notice is that the gas pressure inside of the container is less than the pressure outside. That would be a very, very flat tire if this were a tire. And we can measure this difference in millimeters and then subtract that from the pressure outside, which in this case, if it's 1 atmosphere, would be 760 millimeters of mercury, and then have that would give us the pressure inside in millimeters of mercury. This particular container, though, shows us a gas container where the pressure inside of the container is larger than the pressure outside by this many millimeters of mercury. And so we would say 760 millimeters of mercury plus this difference would tell us the pressure in here in millimeters of mercury. Another way of saying millimeters of mercury, in deference to the inventor of the barometer, Torricelli, would be to call them torr. So that's a unit of pressure. 760 torr is 1 atmosphere. So if you look at this particular container, here's a work example for us. The question is, what is the pressure inside of that container of gas? In order to answer that question, we'd have to know the pressure outside. So let's say the pressure outside is 1 atmosphere. the pressure inside of the container is more than the pressure outside, because notice that this side is pressed down further. There's more pressure acting against this side of the mercury than this side. And the difference is 25 centimeters, which is 250 millimeters. So what we're saying is the gas pressure inside of this container is 250 millimeters of mercury more, stronger than the pressure outside. So if the pressure inside is 760 plus, if the pressure outside is 760 plus 250 is 1010. So the pressure of this gas would be 1010 millimeters of mercury. And that's actually a good spot to pause. So we'll pause here and we'll pick up with Boyle's law in the next video.